Welcome to our next experiment in general physics, which is recreating Galileo's motion experiments. Galileo rolled a ball down an inclined plane to study the motion of the object. We are going to repeat that with a modern piece of apparatus called the air track. Before we get into how you analyze the data and what you do in the lab, let's take a break and go look at how we acquire the data and what the air track looks like.
This is a view of the apparatus that we're going to be using to take the data. It's known as an air track, and at the left you can see a gold glider that sits atop a triangular beam. At the far right you can see a blower assembly, which is black, and that blows air into that triangular beam so that the air comes out through little holes and produces a thin layer of air between the golden glider at left and the track. As a result, all of the friction is essentially eliminated. Now, the air track is sloping downward slightly. It's very difficult to see that here in the picture. If we come in and take a look at the glider sitting there, we can zoom in and see that the front of the glider is sitting at about the 20 centimeter mark. And this is where we will always start the glider. Now right now, because it's noisy, the blower is not turned on. But what we will do is allow the glider to glide down the length of the air track to a variety of different locations. And the distance that the glider has glided is the final location, x, minus the initial location, x. Let us turn on the blower assembly here. And what we can do is turn on the blower assembly. And you'll see that it is rather noisy. And then we can see that our glider is gliding down. And then of course it glides back up. So let us stop our glider. And let us put it at the 20 centimeter mark. And then what we can do is release it and let it go down to, say, the 30 centimeter mark, which would have been back here. And we can time how long it took to go from the 20 centimeter mark down here to the 30 centimeter mark. We time that with a stopwatch. And we do this always releasing it from an initial position of 20, and then we let it glide down, for instance, all the way down here to the 120 position, timing that with a stopwatch. And we can see it bouncing up and down, back and forth here. So once again, we obtain our data by always releasing the glider from the 20 centimeter mark. We zoom in, we always release the glider from the 20 centimeter mark. Start the stopwatch and let it go down to, say, the 60 centimeter mark, and we time that for each different distance: 60, 70, 80, 90, 100, and 120. So we time how long it takes the glider to go from the 20 centimeter mark down to a variety of the other marks. Now you will notice that the glider does not move at constant velocity. That when I let go, it's initially not even moving, and then gradually builds up speed as it goes further and further and further down. And when it comes back up, it gradually loses speed, very much like a bouncing ball. In fact, we'll eventually show that a bouncing ball behaves just like this, except that it accelerates much faster. Our question is, if this is accelerated, is the acceleration constant? And if it is constant, what is the actual value of the acceleration? We'll do it one more time here. We'll release it, allow it to go different distances, and we time it for each of those distances.
Now that we know what the air track looks like and how we acquired the data, let's look at how we determine the acceleration of the glider from that data. Now, the data is provided in the student worksheet as a table. You have x initial in centimeters, x final in centimeters, the change in x, which you have to calculate, the time, which I measured, the average velocity, which you have to calculate, and the final velocity, which you have to calculate. Now, all of the gliders were started at a position of 20 centimeters. That's been filled in for you. The final positions were 30 through 120 centimeters, and so it is necessary for you to calculate delta x. That's quite easy. You simply subtract the initial value of x from the final value of x. We're going to do everything here in centimeters. We're going to stay in centimeters. I want to see in the sample calculation area of your worksheet at least two of these calculations. I don't need to see every single one, but a couple of them is good, with units, units, units. Then you need to calculate the average velocity of the glider on each run. That is simply the change in position in centimeters divided by the time in seconds. Once again, I want to see a couple of sample calculations, centimeters for x, seconds for time, so that the average velocity will come out in centimeters per second, as you see here. So for each row here, for each run of the glider, you calculate the change in position, you calculate the average velocity. Now, the average velocity is not what we need. What we need is the velocity of the glider when it is at the end of its run. Delta x over t gives the average velocity during the run. However, from the equations for constant acceleration, we know that the average velocity is the initial velocity plus the final velocity over 2. And today, we're going to save ourselves the trouble of writing VF every single time, and so we are just writing V. So V with no subscript means V final. Since V initial is 0, we get that the average velocity is the final velocity at the end of the air track divided by 2. Thus, if we double the average velocity, that will give us the velocity of the air track at the bottom of its run. That's what we need, not the average velocity. We need the velocity at the bottom of its run. So you calculate the average velocity. Then you calculate the final velocity by doubling it. Very simple. So you calculate the average velocity by dividing delta x over t. You write that in this column, and then you simply double that to get the final velocity. I want to see a couple of sample calculations. I know multiplying by 2 doesn't seem such a big deal, but I want to see it. And for most of these calculations, 3 significant figures will be more than adequate. Not 3 decimal places, 3 significant figures will be just fine for all of these calculations that you have to make. Once you have determined the final velocity for each of these runs and the time, you then proceed to graph them. You're given a couple of pieces of graph paper. You're given an extra piece of graph paper so that if you mess up, you can go and try again. I highly recommend that you use a sharp pencil when you make your graph. I suggest for this particular exercise that you use what we call landscape mode, that you orient the paper so that it is this way. And you can see I have here on the vertical axis the final velocity v. On the horizontal axis I have the time. Furthermore, I suggest on the vertical axis that each square is 1 centimeter per second. So that you have 1, 2, 3, 4, 5, block, 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 10, block, 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 15, 5, 10, 15, and 20. That'll take you up most of the way vertically, and that's certainly more than halfway. For the horizontal axis, which is the time, I suggest that every 2 blocks be 1 second, so that every little block is a half of a second, and then every 2 blocks you can label like this: 1 second, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or whatever, and you'll see that that takes you here over more than halfway, and so your graph will be occupying more than half of the page vertically and horizontally. It'll be very easy to read. That is what you want to do. Each axis should be labeled with the variable. This is the final velocity, and then we also have the units there, centimeters per second. The bottom is time in seconds. You have a title on your graph, as we mentioned before, and then you plot each of your points very carefully. You plot V, the last column here, versus T. Plot them on the graph. I've only done an approximation here. Then, as we mentioned before, you draw the best fit line with 1 ruler and 1 stroke of the ruler. Don't try and draw 2 lines and make them line up. It just will not work. And that line should extend all the way off the graph in both directions. Be sure to circle your data points, as I've shown there, so that they don't get lost when you draw your best fit line. Once you have your best fit line drawn, and as I mentioned previously, imagine that you're airlifting a piece of roadway here to some pylons that have been driven into the ocean, and you have to take that piece of roadway and somehow lay it down on the pylons so that it balances the best possible. Some might be above, some might be below, some could be on it, it's hard to say, but this is very important to draw your best fit line, and then the center line of the road that you just laid down, that is your best fit line. This is a very sophisticated averaging process. This is called a linear regression. Once you have drawn your best fit line, you now ignore your data points. The purpose of the data points is to get that best fit line. Now you need to determine the slope of that line. To do that, you choose 2 points relatively far apart. They can be outside of the data points if necessary, as long as they're on the line. But the key thing is that you have to be able to read easily and accurately the coordinates of those points. You can usually choose it so that the point is directly on a horizontal or vertical grid line, and then you can find one where you can relatively easily extrapolate and estimate what the other coordinate is. In my case, I just drew this up on the board. Remember that the first coordinate here is the bottom coordinate. This one was for 10 seconds. This is t right, the time for the right slope point. Mark your slope point with an X, as I mentioned. Read off the right time. Read off of the graph the vertical time. This is not perfect because I just sketched it by hand. These have units on them, and you could also write this above. Down here for your left point, here I read off 2 seconds for the coordinates of this one for time, and 4 centimeters per second for the vertical coordinate. This is the velocity for the left point and the time for the left point. Reading the coordinates of your slope points is the most important thing that you do here. This is where mistakes are made. Once you have those coordinates, and again, in the sample calculations area, don't do this on the graph. The graph is just this. The sample calculations go in the sample calculations area of the student report. So you'll have these calculations there, a couple of each of these, so leave room for everything. And then we have to calculate the rise. The rise is the difference between the right velocity and the left velocity. That's the rise of the graph. Show your work. Of course, your numbers are going to be different. Don't try and make your numbers the same as mine, but mine was 21 centimeters a second minus 4 centimeters a second, 17 centimeters per second for me. On another line, calculate the run. This is the right time minus the left time. For me, it was 10 seconds minus 2 seconds was 8 seconds. Show this work. Then you calculate the slope of your graph. The slope is the rise of over the run. For this experiment, the slope is the acceleration. So in my case, the acceleration is 17 centimeters per second divided by 8 seconds. And so the seconds and seconds in the denominator produce seconds squared. And to 3 significant figures, I find that my acceleration is 2.13 centimeters per second squared. And that is the experimentally determined value for me of A. The fact that the line is straight indicates that the acceleration, which is the slope of a velocity versus time graph, a straight line means that that slope is not changing, and that means that the acceleration is indeed constant, and that means that we were correct in using this equation. This is only true if the acceleration is constant. We don't know that at the outset. But once we do the data analysis, we see that the slope is constant. We do get a straight line within, slight variations here. And so that validates our using that. And we found the acceleration experimentally to be 2.13, in this case, centimeters per second squared. The acceleration was measured using a computer as being 2.15 centimeters per second squared. So we can compare our value of the acceleration with the reference value of the acceleration. How close did we come? In my case, you subtract the reference value from the measured value, then you divide by the reference value, and then you multiply by 100%. You must be very careful when doing this calculation. when you enter this into your calculator, either put parentheses around the top, or you can hit A minus A reference and then hit the equal sign to complete that calculation, and then divide by the reference value and multiply by 100%. When I did that, here the units cancel out. We get centimeters per second squared in the top, centimeters per second squared in the bottom, cancel, cancel. So we're left with the pure number times 100%. I got a negative 0.9%. It is perfectly fine to get a negative value for the percent relative error. That simply means that your value was less than the reference value. You probably won't get a percentage this low, but it should be less than about 5%. Graphing is an imprecise technique. And so if you're sloppy, if you don't plot your points real well, if you don't draw the best fit line, more importantly, if you misread your slope points, this will be off by a much larger amount. If this is too large, if this is over about 3 or 5%, you better go back and double check and make sure that you didn't make a mistake somewhere. Well, that's it. That's all we're doing in this. We're trying to determine, do we get a straight line? If we do, that means the acceleration is constant. Did we get a straight line? Well, you kind of know what's going to happen. Also, what actually is the acceleration? Well, turns out to be just a few centimeters per second squared, just a couple of centimeters per second squared. The acceleration due to gravity in these units is about 980 centimeters per second squared. So this is roughly a 500th of the acceleration due to gravity. And that's why we could use a conventional stopwatch to do it. Later, we'll use an electronic stopwatch and actually drop a ball and actually measure the acceleration due to gravity using exactly the same techniques. So if you get this down in this lab, the one that's coming up later on will be almost a carbon copy, except we'll really be measuring the acceleration due to gravity. That's it. Take care. Bye-bye.